Okay, we're going to practice some linearization stuff. So let's say that you are doing an experiment, kind of like the practicum that we did where we had the board and we spun it on the turntable and we put the washers on and you had to figure out which washers would fly off. Well, let's say that you have a bunch of different boards with a bunch of different mu's. Like different material boards, and you want to find the relationship between mu and the velocity that it can spin at some given radius. So maybe at this radius r, where you have the relationship between mu and velocity that it can spin for a given r, because you have all these different materials. So mu would be your independent variable, velocity would be your dependent variable. So to do this analysis, we need to draw a force diagram. If we think about the washer, when it's maybe out here, you would have the force of friction acting towards the center of the circle. Gravity would act down, normal force would act up. This is kind of a side view. Normal and gravity are going to be equal because the sum of the forces in the y direction is equal to 0. And equal in magnitude. And then we can write some of the forces in the x direction is equal to just the force of friction, because that's the only force acting towards the center. So this would be mv squared over r equals mu times mg. And then mass cancels. And so then we have this equation v squared over r equals mu times g. So maybe you're asked, what can we graph to get a straight line so that we could get an experimental value of r? We know that we kept r constant, so r was like a given value, and maybe we want to find the percent error of it for our experiment. So there are a couple of different ways to do this, but what I usually like to do is put this into y equals mx plus b form, because you're trying to graph a straight line. So you're going to need to have the equation look like this. Now we can see that there's not going to be a b in this situation because there's nothing added in the equation, so that b is going to go away. And so we need basically our independent variable equals some constant times our dependent variable. Shoot, I did that backwards. Sorry. Dependent variable equals some constant times your independent variable. Y corresponds to your dependent, x corresponds to your independent. So we can rearrange this equation so that we have our dependent variable isolated. And then when we put it in the y equals mx plus b form, we can see what our slope should represent and what goes on our x-axis. So I'm simply going to multiply each side of this equation by r, and I'm going to get v squared equals mu times g times r. And I know that my dependent variable is v, my independent variable is mu, and then g and r are constants. So that's going to be the slope. I'm going to write this one more time rearranged. V squared equals gr times mu. And this is y equals mx plus b. V is my y, gr is my slope, and mu is my x, my independent variable. So now if I made a graph of v squared and mu, then I would get a straight line, because there is a constant that's relating the two. So if we take our mu values, multiply by a constant, we get v squared. Now to take that a step farther, a lot of times on quizzes, you will have to, quizzes and tests, you're going to have to use the slope in some way. So you have to know what the slope represents. And the way you figure out what the slope represents is to do this, to put it into y equals mx plus b form. Whatever constant is multiplied by your x variable is going to be your slope. So this slope is g times r. So let's say that we do this. We get our scatter plot, and I'm not going to actually do this with numbers, but we get a line of best fit here, and we find the slope. We find the slope by taking change in y over change in x. And let's say that we have something like 20, let's see. Let's say we have like 2.5 meters squared over seconds squared, because that's the unit of our y-axis. That's our change in y. So maybe we like find 2 places where our line crosses the hash marks on our graph. Remember, you don't want to use data points unless they go directly through your line of best fit. You're using points on your line. And then we divide by 0.5, which is like our change in mu. Mu doesn't have units, so that's going to be unitless. So we get 2.5 divided by 0.5, and that gives us 5 meters squared over seconds squared. That is our slope. Well, now, if I'm using my slope to find my experimental value of r, then I'm going to set my actual slope equal to what my slope is supposed to represent. So I have 5 meters squared over seconds squared is equal to g times r. And I know g is 9.8 newtons per kilogram, so I get 5 meters squared per second squared equals, I'm going to use 10 for easy mathing, 10 times meters, sorry, I did that backwards. Meters per second squared is our unit of g. We can do newtons per kilogram, or we can do meters per second squared, times r. When I divide each side by 10, I get r equals 0.5. Seconds squared would cancel, one of the meters would cancel, and the unit is meters. So that would be my experimental value for r in this situation, and then I could find a percent error if I wanted to. So that's one way to go about this. Let's look at another way to go about this. Some people prefer to always isolate their dependent variable. So if I had this equation, maybe I derived it, or maybe it was given to me, v squared over r equals mu g. I want to put it into y equals mx plus b form. And I want to isolate my y variable. And since v is my y variable, I'm going to isolate it. So I would have v is equal to mu times g times r, sorry, v squared. And then I'd square root both sides. So I get v equals the square root of mu g r. So now, if I wanted to put this into y equals mx plus b form, it helps to separate the m and the x. So separate your independent variable, which is mu, from the rest of the things which represent the slope. So this would be v equals the square root of g times r times the square root of mu. So this is your equation. This is my y, v is my y, this is my slope, and this is my x, my independent variable. So I could also linearize this by graphing, let's draw this over here, v and the square root of mu. And that would also give me a straight line. But my slope would represent something different than it did over here. Now my slope is going to represent this constant, which is the square root of gr. So I could do this whole process again that I did down here, where I find the slope using 2 points on my best fit line, not necessarily 2 data points, unless the line goes through those data points. And then I set that slope equal to the square root of gr, and I solve for r, and then I get my experimental value of r. So when you have a situation where you're asked what you would graph to make a straight line, use the equation that you have and manipulate it until you get it into y equals mx plus b form. And then look at what is being done to each of the variables. So like this one, you have v and the square root of mu, so that's what you put on your axes. This one down here, you have v squared and mu, so that's what you put on your axes. Happy graphing!